Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study the division algorithm in polynomial rings. We have studied earlier division algorithm for integers. That means when one integer is divided by another non-zero integer, we get a pair of integers that are denoted as quotient and remainder. Also we know how to divide polynomials, and the same process is expressed here as the division algorithm. I have written here theorem. First we shall see the statement of the theorem, and then we will illustrate this statement of the theorem by means of this example, and then we shall prove the theorem. The statement of the theorem is, let f of x be a polynomial ring. We have studied in our earlier lecture what is a polynomial ring. It is set of polynomials and whose coefficients are the elements of this field. Here we consider f as a field. F of x is polynomial ring over field f, and we take two polynomials. Given two polynomials f of x and g of x, this is non-zero. G of x is not equal to 0 in this ring of polynomials. Then for these two polynomials f of x and g of x, there exist uniquely two polynomials q of x and r of x in f of x, such that the relation between these is f of x is expressed as q of x into g of x plus r of x, where the condition on r of x is either r of x is 0 or degree of this r of x is strictly less than degree of g of x. Degree means the power of highest coefficient, highest power in the polynomial is the degree, we know. And this is the division algorithm. That means given two polynomials f and g non-zero, g is non-zero, there exists a pair of polynomial qx and rx such that f of x is written in this form, and where the condition for r of x is like this. Now we shall illustrate this process of division algorithm. We know already we have divided one polynomial by another polynomial earlier in school mathematics. The same example I have written here for illustration of this division algorithm. We shall take f of x as 6x cube minus 2x square plus 3x plus 2. This is a polynomial of degree 3. And g of x is written as 2x square plus 3x minus 4. Any example can be taken. And now here we shall divide f of x by g of x. This polynomial f of x is divided by g of x. Now how the quotient is formed? The first term in the quotient I have written here 3x. Now that is easy to get. So what we shall do is 6x cube, that is first term in f of x, is divided in by the first term of g of x, that is divisor, and what we shall get, this is 3x, and therefore this is the first term in the quotient. And once this is written here, we multiply these two and the product is written here, that is 3x into 2x square 6x cube plus 3x into 3x, that is 9x square, and etc. That is minus 12 into x. Now these are subtracted, and this term is equal, and therefore its subtraction is 0. Minus 2 minus 9 minus 11x square, 3, and this minus of minus becomes plus 12, 15x, and this 2 is taken further. And now for the next term of the quotient, here it is minus 11x square, and that is the first term here, and the first term in the divisor is 2x square. So here what is the division is minus 11 by 2, and that is to be taken as second term in the quotient. And now the product of these two is, this is the process of division, we know, is written as minus 11x square, this is minus 33 divided by 2, and this becomes plus 22, and again these are subtracted, this is 0 minus plus 15 plus 33 by 2, that is this much 63 by 2 x, and this is 2 minus 22 is 20. And now you see the degree of this expression or this polynomial is strictly less than the degree of this gx divisor, and here the quotient, the division stops, division process stops. And now we express this division as this is the dividend and this is the divisor, and that means this is f of x, this is f of x, this is g of x, and we denote this by q of x, quotient, and this by the remainder r of x. And the relation between this f, g, q and r is this f of x is equal to product of these two, that is qx and gx, 3x minus 11 by 2 into this g, and plus this remainder, that is 63 by 2 x minus 20, or that means we have here as you see. Therefore, this is f of x is equal to, this is q of x and this is g of x plus this is r of x. What is the condition in the theorem? Rx is 0 or either 0, or if the division is complete, or that means it is actually this polynomial divides the other polynomial, that is gx divides fx, then remainder will be 0. Otherwise the degree of remainder is less than degree of g of x. And here the second condition satisfies, where degree of, and we denote degree in short like this, deg of r of x is less than degree of g of x. That is, what is g is this is the first degree and this is second degree. So thus this is the process of division algorithm that is written in this statement of the theorem. Now we shall prove it. So this is the illustration how the quotient and remainder is obtained by actual division. Now we shall prove the theorem. To write the proof, we will consider these two polynomials f of x and g of x. Let f of x, g of x, actually it is given in the theorem, belongs to the polynomial ring f of x, and further let f of x be a polynomial of degree m, and we know we have written this as in our earlier lecture as a naught plus a1x plus so on up to am x power m. Here am is not equal to 0, and therefore here the degree is m. It is non-negative integer and it is the highest power of x in the expression in the polynomial. And gx we write as the coefficient, we write b naught plus b1x and plus so on up to bn x raised to n, and this is of degree n where bn is not equal to 0. These are the two polynomials. Now first case or we shall consider is what happens if degree of fx is less than degree of gx, and what is the degree of f is m, then degree of f of x is equal to m and degree of g of x is equal to n. So first case we have is if m is less than n, that is degree of f of x is less than degree of g of x, then the theorem is obvious. This theorem is obvious. Theorem is obvious, or actually there is nothing to prove. It is trivial. So how? Now I shall rub out this. See, in this case we shall consider the quotient as 0 and remainder as f of x itself. We take here we take q of x is equal to 0 and r of x is equal to f of x. So see, and then what will be this theorem? F of x, then f of x is equal to 0 into g of x. Q is 0 and r is f, plus f of x, where the degree of r of x, which is f of x, is less than degree of g of x, where degree of f of x is less than degree of g of x, and thus the theorem is verified. It is obvious. So now, therefore, we consider another possibility, that is, if m is less than n, the theorem is true. Now, what is remaining possibility? M is greater than or equal to n. Now, suppose m greater than or equal to n. So, this is the second case we shall consider. And in this case again also, if m is equal to 0, that means degree of f of x is equal to 0, then what will happen? If m is equal to 0, then this is 0, then 0 is greater than or equal to n. 0 greater than or equal to n implies n must be 0, because n cannot be negative, n is non-negative, and therefore and n is again less than or equal to 0, means n cannot be less than 0, therefore n must be 0, and thus both are 0. M is 0, then n is also 0, and thus the degree of f is 0 and degree of g is also 0, means both are polynomials of degree 0, and therefore both must be constant, non-zero constant. Then f and g, therefore fx and gx are of degree, are of both are of degree 0. And thus if this is of 0 degree, then fx will be a naught, because x term, these all coefficients will be 0, and g of x is constant, both are constant of degree 0, and gx will be b naught. Then f of x is equal to a naught and g of x is equal to b naught, where both are non-zero. A naught is not equal to 0, b naught is also not equal to 0. Here what we can do is, we can write, in this case we have to verify the theorem. We can write, or we have, see, f of x is equal to a naught, and this a naught can be written as a naught b naught, inverse of b naught into b naught plus 0. And you see, a naught is equal to a naught b naught in inverse into b naught. This is 1, and this is, whole term is a naught, and remainder is 0. That is, this can be taken as q of x, and b naught is g of x, and this is r of x. The remainder is 0, where r of x is equal to 0 and q of x is equal to a naught into inverse of b naught. Hence, the theorem is true when m is equal to 0. So, this proves the theorem for m is equal to 0. So, this shows that the theorem is true for m is equal to 0. That is, the theorem is true when m is less than 1. That is, m is equal to 0. That is when m is less than 1. Now we shall prove the theorem by the method of mathematical induction. We have here proved that the theorem is true for m is less than 1, and that means we shall assume that the theorem is true for when the degree of f of x is less than m, and then assuming that we shall prove the theorem is true for when degree of f of x is equal to m, and thus this is the method of mathematical induction. When we prove a result for a certain value, and then we shall prove the result for next value, next higher value, and then the result becomes true for all values. And so we shall prove the theorem. So we shall use that method of induction here. We shall prove the theorem by the method of mathematical induction. Assume that the theorem is true for degree of f of x less than 1. Then we shall prove that or we shall show that the theorem is true when degree of f of x is equal to m. So this is the method of induction. Assume the theorem is true for when degree of f of x is strictly less than m, and show further step is show, assuming this, show it is true for the next value which is m. Then it becomes true again for next higher value, that is m plus 1, and once it is true for degree m plus 1, it will be true for again degree m plus 2 and so on. It becomes true for all degree. So, and now we shall consider a function f1 which is having degree less than m. Let f1 of x is equal to, how this polynomial is formed, it is f of x minus am upon bn multiplied by x power m minus n into gx. Now we can verify this expression. So what we have written is f of x and g of x we have already written as polynomials of mth degree and nth degree, and their actual expressions also we have written. See what will be this expression. We shall see what is f of x, then this f1 of x will be, actually we shall only verify this. F of x is a naught plus a1x and so on, am x power m. This is f of x minus am upon bn into x power m, I shall write below, minus am upon bn into x power m minus n into gx. What is gx? b naught plus b1x plus so on up to bn x power n. Now you see their difference. Here we can observe the first term of this product, bn, and this is multiplied to every term, but we shall verify the last term into this term. Here this bn cancels, and x power m minus n multiplied by x power n means it becomes x power m and multiplied by am. So therefore this term am minus am x power m minus am x power m, product of this cancels. So this term being cancelled with this term, and thus the degree becomes less than m of this expression. Here m is greater than n, so we have assumed, and that is m is greater than, our possibility is m is greater than or equal to n, and therefore here this mth term vanishes, and if mth term vanishes, the degree of this expression becomes less than m, and therefore here we have degree of f1x is less than m. Then degree of f1x is less than m, certainly less than m, because the last term of this expression gets cancelled, and remaining expression will be having degree less than m. You may verify this. And now if it is of a degree less than m, by our assumption, what we have assumed is, when degree of f of x, a polynomial, or it may be f or any other polynomial, if degree of that polynomial is less than m, the theorem is true. And here degree of f1x is less than m, so therefore the theorem holds for f1x. So therefore the theorem is true for f1x by our assumption. And thus what the theorem is true means there exist two polynomials. Now we shall denote it by q1 and r. Therefore there exist two polynomials q1 of x and r of x. Second polynomial we write as the same notation, r of x, in f of x in the ring of polynomials, such that this f1 is written as, we are applying the theorem for f1. f1 is equal to, f1 of x is equal to q1 of x into g of x, and plus r of x, where degree of r of x is 0, or degree of r of x is strictly less than degree of g of x. So we have applied, the theorem is true for f1 and g of x. We can write f1x and g of x. And therefore there exist polynomials, two polynomials q1x and r of x in f of x, such that this f1x is equal to q1x into gx plus r of x. Now what we shall do is, we shall write this expression for g of x, f of x, and now this is f1 is equal to f of x, this expression f1 here on the left side of this equation. So we may suppose this as 1, then by 1 we will have f of x minus am upon bn into x power m minus n into g of x. This is the expression for f1 we have written here, and right side is the same, q1x g of x plus r of x. This we will have, and you see from this we shall write the expression for f of x. We want to write expression for f of x, and that expression can now be written as f of x. F of x is equal, we shift this term on that side, and that will be am upon, it will be positive now, am upon bn into x power m minus n times gx, and this gx and gx is common expression, so we shall write it common. This is shifted on right side, and this is plus q1x multiplied by g of x. You observe this expression is shifted on right side, it becomes positive, and g of x we have written common. plus r of x. And now this is in the same form as f of x is equal to q of x gx plus r of x, where this expression is q. And what is the condition for r? It is the same. So that is f of x is equal to q of x into g of x plus r of x, where r of x is q of x is the bracket expression in the bracket. Is am upon bn into x power m minus n plus q1x, and degree of r of x is 0, or degree of r of x is less than degree of f of x. And this proves the theorem is true for degree of f of x which is equal to m. Thus the theorem is true when degree of fx is equal to m. Thus there exist q and g in f of x satisfying this condition. Thus there exist qx and rx in fx, satisfying the condition in the theorem. So this proves the first part, that is existence. So what we have proved is there exist the two polynomials qx and rx satisfying this equation and this condition on r of x. Now what remains to prove is the uniqueness. These two polynomials, which is generally known as quotient and remainder, are unique, and that we shall now prove. Uniqueness of q and r. That means the quotient and remainder is only one. There cannot be two quotient, two remainders, etc., or more than one. It is only one, more than one does not exist. That we have to prove. Now suppose, if possible, there exist two such polynomials, that is q1, q2, r1, r2, which satisfies the theorem. Suppose, and we shall write directly like this: f of x is equal to q1 x into g1x g of x plus r1x, and this is equal to second case we shall write as q2 of x into gx plus r2x, where we are satisfying the theorem. The conditions of the theorem means degree of r1 is 0 or degree of r1 is less than gx. Similarly for r2, degree of r2 is 0 or degree of r2 is less than degree of gx, satisfying the conditions of the theorem. Then what, from this equation what we can write is, therefore see, we shift this g of x on left side and we shift this r1 on the right side, and then that can be written as q1 of x, g is common, minus q2 of x multiplied by g of x this is taken on left side and is equal to, if this shifted on right side, it becomes negative. R2 of x minus R1 of x is the equation that we shall get. Now we shall assume this equation as second. And now what happens if this is not 0? If this first bracket is not 0 and by assumption the second is not 0, then if both are not 0, the product is not 0. This is the property of integral domain. And this f of x is also integral domain because the coefficients are elements of field, and therefore f of x is integral domain. That condition we shall use here. So if this q1x minus q2x is not equal to 0, then and as g of x is not equal to 0 is given, we have this product is not 0. q1x minus q2x into g of x is not equal to 0. And if this product is not 0, and then what about degree of this? The degree of this product. Now we know the degree of g of x is, here the condition is given, g of x is not equal to 0. Therefore, if this is not 0, then this is not 0, the left side is not 0. So we have this expression. Then further, q1x minus q2x, or we shall write degree of this. Therefore, degree of this expression q1x minus q2x into g of x is greater than or equal to n. Or see why this is so, because the degree of g is n, and therefore if degree of product of two polynomials is addition of the degrees. So this is n plus this number, which may be 0 or greater than 0. So therefore this will be greater than or equal to, strictly greater than or equal to n. And but now what is the condition on the right side? But degree of R2x minus R1x. Now this is the difference of two polynomials. And what is the condition of on this R1 and R2? Their degrees are strictly less than g. Degree of R1x is less than g, it satisfies the condition of the theorem. So degree of R1x, R2x is less than degree of g, that is n. Degree of R2x is also less than, R1x is also less than n. Means degree of both these polynomials is less than, strictly less than n. And therefore their difference will be, degree of their difference will be also strictly less than n. So thus when this equality equation will be true, here their degrees must be the same, then and only then it will be equal. And that in that case, see, it will be equal only if the both sides are 0. Then and only then this equation will hold. So therefore equation, the equality of equation 2, otherwise it will not be true. Equality in equation 2 will hold. Only if both sides are 0. But the left side, you see, this g cannot be 0, and therefore this must be 0. If will hold only if q1x minus q2x is equal to 0 and r1 of x minus r2 of x is equal to 0. And therefore what we shall get, this is q1 of x is equal to q2 of x, and r1 of x is equal to r2 of x. So this proves the uniqueness. That means the quotient polynomial is unique and the remainder polynomial is also unique. We assumed here two expressions for f of x in different quotient remainder, but they are equal. That we have proved, and hence q and r are unique. So this shows that qx and rx are unique. These polynomials are unique in f of x, and this completes the proof of the theorem. We have proved first a part existence, there exist these two polynomials, and next we have proved they are unique. So this completes the proof. So thus in this lecture we have studied what is the division algorithm in polynomial ring, taking first as illustration, and then we have proved the theorem. I hope you can understand the theorem. Thank you for watching the lecture.